Hello everyone. Welcome to the Fundamentals of Analog Electronic Technology course. In the previous lesson, we studied the structure and operating principle of the MOSFET. In this session, we will continue our study of MOSFETs and related topics. In today's lecture, we will cover the IV characteristic curves and characteristic equations of the N-channel enhancement mode MOSFET, the N-channel depletion mode MOSFET, the P-channel MOSFET, the channel length modulation effect, and the key parameters of MOSFETs. Drain current, voltage characteristics, and characteristic equations of the N-channel enhancement mode MOSFET. Output characteristics and characteristic equations. When V sub Gs is held constant, the drain current I sub D is a function of the drain source voltage V sub Ds. Based on this function, one can plot the output characteristic curves of the enhancement mode NMOS in the coordinate system with V sub Ds on the horizontal axis and I sub D on the vertical axis. Cutoff region. When the gate source voltage V sub Gs is below the threshold voltage V sub Tn, no conductive channel forms, so the drain current I sub D is 0. The transistor is in cutoff, and this region of the characteristic curve is called the cutoff region. Variable resistance region. To the left of the pinch-off locus above the horizontal axis lies the variable resistance region. The operating conditions in this region are: gate to source voltage V sub Gs is greater than or equal to the threshold voltage V sub Tn, and drain to source voltage V sub Ds is less than the difference between V sub Gs and V sub Tn. According to the IV relationship in the variable resistance region, the behavior can be described by a characteristic equation. When V sub Ds is relatively small, the V sub Ds squared term in that equation can be ignored, and the drain current I sub D is approximately linear with respect to V sub Ds. The slope of the characteristic curve in this region is the output conductance, whose reciprocal is the port resistance. By differentiating the characteristic equation, one obtains the small signal port equivalent resistance R sub DSO, which shows that R sub DSO is a voltage-controlled resistor governed by V sub Gs. Given different values of gate-to-source voltage V sub Gs, different drain-to-source resistances R sub DSO arise, which is why this region is called the variable resistance region. A MOSFET operating here can be used as a voltage-controlled variable resistor. This is also the most important characteristic of the variable resistance region. The parameter K sub n in the characteristic equation is called the transconductance constant of the N-channel field effect transistor. Its value depends on the device's fabrication parameters. The saturation region is also called the constant current region or the amplification region. In the output characteristic plot, above the horizontal axis and to the right of the pinch-off locus is the constant current region, also called the amplification region. The operating conditions in the constant current region are V sub Gs greater than or equal to V sub Tn, and V sub Ds greater than or equal to V sub Gs subtract V sub Tn. The voltage-current relationship in this region can also be described by a characteristic equation as shown in the figure. I sub D0 is the drain current when V sub Gs equals twice the threshold voltage. Therefore, when using a FET to amplify a signal, it must be biased in the constant current region. For this reason, the saturation region is sometimes simply called the amplification region. Transfer characteristics. The transfer characteristics describe the relationship between the input port voltage V sub Gs and the output port current I sub D. In the constant current region, I sub D is controlled by V sub Gs. Using the voltage current expression for drain current and gate to source voltage in the constant current region, as shown in the figure, One can plot the transfer characteristic curve of I sub d versus V sub ds at V sub ds equals 5V. This is a quadratic curve. It is also possible to obtain the transfer characteristics by graphical construction from the output characteristic curves. N-channel depletion mode MOSFET. Structure and operating principle. This is the structural diagram of the N-channel depletion mode MOSFET. The silicon dioxide insulation layer is doped with a large number of positive ions, forming an existing conductive channel. It can operate under positive or negative gate-to-source voltage, and there is virtually no gate current. This is the electrical symbol for the N-channel depletion mode MOSFET. The arrow from the substrate points into the N-channel, and the drain, substrate and source remain connected, indicating that the channel is already on at zero gate bias. This is the characteristic equation of the N-channel depletion mode MOSFET in the constant current region. I sub DSS is the drain current at zero gate bias, called the saturation drain current, and corresponds to the intercept of the transfer characteristic curve on the vertical axis. VPN is the threshold voltage of the N-channel depletion mode MOSFET, distinct from the threshold voltage V sub Tn in the enhancement mode MOSFET's equation. From the output characteristic and transfer characteristic curves of the N-channel depletion mode MOSFET, the following features emerge. The channel exists inherently. When V sub Gs is given a positive voltage, the channel widens. When V sub Gs is given a negative voltage, the channel narrows. If V sub Gs falls below VPN, the induced channel disappears and the FET turns off. From the transfer characteristic curve, it is clear that VPN is negative. Therefore, we conclude that this type of MOSFET can operate under both positive and negative gate-to-source voltages. P-channel MOSFET. Unlike NMOS, the substrate is N-type and the channel is P-type. This reverses the polarity of the applied voltages in operation, and the conventional current flows out of the drain. For example, an enhancement mode PMOS enters the constant current region only when a negative V sub Gs is applied. This is an enhancement mode PMOS. This is a depletion mode PMOS. This is the output characteristic curve of an enhancement mode PMOS. This is the transfer characteristic curve of an enhancement mode PMOS. In both figures, the positive current reference is taken as flowing into the drain terminal. Channel length modulation and other effects. Channel length modulation effects. From the output characteristic curves shown in the figure, we observe that the curves in the saturation constant current region are not actually flat but instead slope upward. Therefore, the saturation region current voltage equation must be modified to include the channel length modulation parameter lambda. Taking an enhancement mode NMOS transistor as an example, the corrected formula accounting for channel length modulation is presented in the figure. Extending the slope traces leftward, they intersect the horizontal axis at a negative voltage V8, called the early voltage, equal to -1 over lambda. When the channel length modulation effect is ignored, lambda equals 0. The curves are flat. Breakdown effects. Drain to substrate breakdown. If the applied V sub ds is too high, the PN junction between drain and substrate avalanches, called drain to substrate breakdown, gate oxide breakdown, with an oxide thickness of 50 nanometers, about 30 V across the gate can puncture the oxide. With a safety factor of 3, the maximum safe gate voltage is only 10 V. In practice, a bidirectional TVS diode is usually connected between gate and source to clamp the gate voltage and protect the device. Let's get a summary. This lesson covered the characteristic curves and equations of various FET types, as well as effects such as channel length modulation. These are the key points of today's lesson. Thank you.